Hey, this is Josh. So in this video, we're going to do temperature unit conversions. We're going to have 3 example problems in the middle of this video, and then at the end, I'm going to explain why we have 3 different temperature scales used in science, at least in the United States. All right, so first, you can just pause this video whenever, but I have written various temperature conversions. All right, I have 6 different conversions to show. Okay, I have 4 in this first page. All right, so for these top 2, this is if you have a Celsius temperature to put in and you want to get a Fahrenheit temperature out. Okay, you can see TC, you put it in, you get a TF Fahrenheit temperature out. Okay, so this reads TF equals 1.8 TC plus 32. And you would multiply the Celsius temperature by 1.8. Okay. Some like to write this same expression this way. Instead of using a 1.8, you used a fraction 9 over 5, 9 divided by 5 being 1.8. So these two expressions are identical to each other. Okay, this is a similar expression in which you're putting in a Celsius, but instead of a Celsius, or excuse me, instead of getting a Fahrenheit, you're going to get the Kelvin temperature out, okay? So the temperature in kelvins is equal to the temperature in Celsius plus 273.15. All right. What we have for these two conversions at the bottom is this is just the reverse of this one, where we put a Fahrenheit in and we would get a Celsius out. This reads Celsius temperature equal to the Fahrenheit temperature minus 32, and that whole quantity in parentheses being divided by 1.8. Make sure you use the parentheses if using this expression, because otherwise the 1.8 will divide only into the negative 32. In other words, that changes it, and that's not good. That's wrong, okay? And this is an alternative way of writing that expression. All right, and lastly, we just did the reverse of this one. So the Celsius temperature is equal to your Kelvin temperature minus 273.15. Okay, so these two expressions are basically the same except adding versus subtracting. Okay, pause this video if you want to write this down. I'll give it a few seconds. Okay, all right, so there's 2 more conversions I can go over here. All right, and that involves going from Fahrenheit to kelvins or the other way around. Okay, I show a little bit of the algebra involved here if you want to take a look, but here's the summary. All right, the Fahrenheit temperature, to get this expression is for if you put the Fahrenheit temperature in and you want to get out a Kelvin temperature. Okay, so we have parentheses TK equal to parentheses TF plus 459.67. Yeah, a little bit of a crazy number. Some people would just write 460 instead, but this is the most accurate and precise number. If you need that, close the parentheses and then divide the whole expression by 1.8. Okay, lastly, we just do the reverse of this formula. And if you need to put in a Kelvin and get out a Fahrenheit, if you're needing a Fahrenheit, the Fahrenheit temperature is equal to 1.8 times the Kelvin temperature minus 459.67. And I'll pause a few seconds if you need it. All right, cool. All right, so before we do some example calculations, I thought it'd be just kind of give a good idea to give some context to these numbers. All right, if you're in the United States like me, you might be most familiar with Fahrenheit. Our weather is usually done in Fahrenheit, so on and so forth. Okay, I try to come up with some silly rhymes. I saw this Celsius rhyme on the internet somewhere. Here, let me grab. There it is. The citation, if you need that, I'll also put it in the description. All right, so for people unfamiliar with Celsius, the rhyme goes 30 is hot, 20 is nice, 10 is cold, 0 is ice. So I thought that was pretty clever. It rhymes and helps you remember that. I try to come up with something with Fahrenheit. You can be the judge of if I'm a poet or not, but I'll just let you read that. The one that I'm more proud of is what I came up with Kelvin. All right. A lot of people coming into chemistry class, an intro chemistry class, they may not be too familiar with Kelvin or not at all. Okay. Kelvin is used in a variety of scientific applications. For me, especially for Chem 101 students, I think where you're going to see Kelvin be most useful in the future is going to be for gas calculations, gas laws. Basically, the Kelvin temperature scale allows for or doesn't allow for negative numbers. It makes negative numbers impossible. The lowest temperature possible in the Kelvin scale is 0, which we know to be absolute 0, when nothing is moving at all at the atomic level. All right, so for Kelvin, you add 273 to the 1 with the C, add 0.15 if precision you strive. That's my little rhyme for today. All right, so let's get into some calculations. All right, so let me put this away, and we're going to get into some calculation examples. Okay, I'll explain the thermometer stuff in a little bit. Okay, if you want my little preview, there it is. All right, but before I get into the theory, a lot of people, and I imagine most people watching this, just want to see some calculations in action. So, all right, so we're gonna have 20 Celsius. We're gonna convert that into Fahrenheit. Second example, we're gonna do negative 40 Fahrenheit into Celsius. And then the last example, we're gonna do 20 Celsius into Kelvins. I chose these two, 1 and 3, because 20 degrees Celsius is a very typical lab temperature, right? Okay, so give you a minute to write that down. Oh, wait, I'm a recording. I don't need to give you a minute. All right, let's just dive into the work. All right. So my example problems generally in this course, at least my current plan, is to not pre-write too much. I want you to get a feel for how much time someone spends to write out and do these calculations. It's not some automatic process, okay? I think there's a lot of value in writing, so I'm going to lead by example there. All right, so example 1. We wanted 20 degrees Celsius converted into degrees Fahrenheit. All right. If you have not heard of sig figs yet, significant figures, significant digits, that's fine. We're gonna talk about that later. If you've heard of it and you're concerned about it, I'm not going to be following sig fig rules for the purposes of this video. Okay. If you have no clue what I'm talking about, we're good for today. All right. Okay, so go ahead and try to tackle this. Okay, let's do this. All right, so first order of business is you're going to want to grab the correct formula. All right, I got a lot of papers lying around here. Let's see. This one, nope. There we go. All right, let's grab the correct formula. So we were given a Celsius, and we need to get out a Fahrenheit. So this one here is going to be perfect. Celsius in, Fahrenheit out. All right. Plug in the 20. So step 1, write out the formula. Step 2, put in the 20 for the Celsius. Number 3. Ooh, glare. There we go. And we got 36 for this expression. Let's see if turning off the light improves the glare issue. I'm going to leave it back on. All right, and we're almost done here. 36 plus 32 is going to be 68. All right. And we were looking for a Fahrenheit, so we can label the answer degrees Fahrenheit. And I recommend boxing, circling, doing something of that nature for your answer. Okay. Okay, so 20 degrees Celsius is 68 degrees Fahrenheit. Personally, for me, this is my favorite temperature. I am perfectly happy at this temperature. All right, let's go on to example number 2. And that problem was negative 40 degrees Fahrenheit. Let's figure out what that is in Celsius. And I gave a little hint of I was trying to be a little bit funny here. All right. Pause this video to work on that. 1, 2, 3, 4, 5. All right. Let's go for it. So the formula we need. Okay, we don't want this one this time. Although we're working with Celsius and Fahrenheit, and both of these do that, this is putting in a Celsius and getting out a Fahrenheit. We were given a Fahrenheit, and we're looking to get out a Celsius. So this one isolates the Celsius. Okay, step 1, always write the equation. Step 2 is plug in the number. Remember that it's negative. Step 3, let's do the part in the parentheses. Negative 40 minus 32 should come out to negative 72. I'll just do that on the calculator. Some people just always want to see it on the calculator. Using a calculator like mine, I have to make sure to hit the negative button instead of the subtraction operation. Negative 40 minus 32. I get negative 72 at the top. I have 1.8 still at the bottom. I can take that answer and divide it by 1.8. And I get negative 40. And we were looking for Celsius. And so that is our answer. Okay. So yeah, I was trying to be funny because this and that, you're like, wait, did I do something wrong? I got the same number. Yeah, no, you did not do anything wrong. This is correct. Negative 40 Fahrenheit. It's the same temperature as negative 40 Celsius. It ends up being the same number, which is pretty cool. Regardless of your preferred temperature scale, that is really, really, really cold. To most of us anyways. All right, cool. For those who like to think of things in very mathematical terms, I think it's something along the lines of if you were to plot that line versus this line, the intersection point between the two lines would be at a negative 40. All right, let's do the final example. And that's going to be the the positive 20 Celsius being put into Kelvin. All right. Pause for a moment. 3, 2, 1. All right. Oh, I should have showed which formula I'm grabbing. Okay, I know to grab this formula because we were given a Celsius and we want to get out a Kelvin. Okay, we wrote the formula. Plug in the number. Okay, and there's our answer. Note that with Kelvin, we don't write a degree symbol. Depending on your instructor, some, I don't know, maybe they'll get really angry if you do that. If I see a student do that personally for me, I don't really care. Maybe I'll just go like that, make a little mark. But if I remember correctly, whereas Celsius and Fahrenheit are they're a scale with negative numbers possible. With the case of Kelvin, as you'll see in a minute, Kelvin, there's no negative numbers possible. So we don't have degrees because it's an absolute scale. There's no negative numbers possible. Something like that. If you want to read up on that, feel free. Okay. All right, cool. So those were our examples. Now, I promised that at the end of the video, I would do a little bit of background of why 3 different temperature scales exist, okay? The long story short, the reason why that exists is if you look a little bit at history, there's a rationale for each, right? So while I pull up the paper, I'll just kind of tell you a little bit. The Fahrenheit scale came first. The Celsius scale came second. I'd like to edit this out. Okay, I got it. All right. So Fahrenheit first, Celsius came second, and then Kelvin came last. All right. So to explain the different temperature scales, I'm going to talk about thermometers. All right. Thermometer, and you stick it into a substance, it tells you the temperature. All right. So before we even think about different temperature scales, different units, all that sort of thinking and anxiety, I want to just get really fundamental here, all right? What is a thermometer? Okay, thermometer is just something filled with some stuff, okay, where you stick into a substance, you're going to have the liquid in there expand if it's getting warmer, and it's going to cool, it's going to contract when it gets cooler, all right? So you have expansion when hot, contraction when cold. All right, and then there's just markings on it to tell you what your measurement is, okay, and in whatever unit you're working in. All right, so a thermometer doesn't care what unit you're in. It's just, this is just pure physics, pure chemistry. Expansion when hot, contraction when cool. That's all it does. Okay, the markings we put on it, that's just something we decided as humans to do. All right, so to try to really illustrate this point, we're imagining that we have 3 different thermometers on it, okay? Before we put any markings on the thermometers, okay, they're all made exactly the same way, okay, filled with, or made with glass, okay, same exact glass, same exact everything, filled with the same fluid. Many thermometers nowadays are filled with some sort of alcohol that's been dyed red. You can get mercury thermometers, whatever. Okay, but these are the 3 same thermometers. All right. But they have different markings on them, but they're all doing the same phenomenon. All right. So what I want to show you, and this is kind of the parting thought, if you were to do any sort of temperature conversion, okay, between the 3 different scales, again, let me bring these back out. Okay, if you were to use any of these 6 formulas, you would be able to see how each of these are actually the same temperature. Okay, it's the same thing. We are at absolute 0 here. No atoms, molecules, whatever are moving at this temperature. Okay, absolute 0. No thermal motions. Okay, no vibrations, no rotations. Okay, no thermal motions. All right. Okay. And then same thing, okay? If we were to be at the melting point or freezing point of water, all right, we would get these temperatures, and then same for the boiling point, all right? Where I want to end this video is kind of giving a story for each temperature scale. So like I said earlier, Fahrenheit came first. And my little bit of reading on the background of Fahrenheit, all right, he was developing a temperature scale, and to kind of get a cold temperature reading, there's various takes I was looking at, but one take was sticking his contraption out on a cold day, and the cold day measured somewhere around 0. All right. Now for when so he thought, okay, cold day should be to 0. Now you don't see me writing a 0 on his Fahrenheit. That's because in hindsight, maybe it's not overly significant on the Fahrenheit scale. Okay. Fahrenheit was living in Poland. All right. And so I guess it was below freezing that day because he was measuring at 0. Okay. So based off of that, later he observed water was freezing or melting around 32 on the scale. Okay. And then based off of how things were going, the boiling point of water ended up being around 212. Okay. And then something else I read was something about how around 90 degrees was like the body temperature. So long story short, I think the two main things that went to Fahrenheit were the body temperature being around 90s and a really cold day in Poland being around 0. And then that ended up being the mathematics of this Fahrenheit scale, and that went through maybe some revisions. Okay. But Fahrenheit, okay, it was the first scale made. Okay, so it kind of has that first mover's advantage in terms of our consciousness of temperatures. All right. So at the end of the day, for Fahrenheit, the good things to kind of keep in your head. I don't know if you necessarily need to memorize it. Not a bad idea, though. 32 freezing, 212 boiling. Now you use the equation, okay? Absolute 0 for Kelvin is a 0. You put it in, 0 times 1 point is 0, and you can see how we get that negative 459.67 as that lowest temperature possible when nothing is moving. Okay. Before we go to Celsius, maybe my parting thought, I still like Fahrenheit, me personally, maybe amongst others in, not just the scientific community, but worldwide. Maybe they feel like Fahrenheit's not necessary because nowadays Celsius does everything that Fahrenheit does. I think, yeah, you probably have a point. If Fahrenheit was done away with, like if the whole world decided we're done with Fahrenheit, I think I would kind of just shrug my shoulders and get used to it using that poem we saw earlier. But, I like using it for weather. I don't really got any issues with it. But in the lab, yeah, I'm definitely these two. Okay. So why was Celsius made? Okay, Celsius at first was called centigrade. Okay. Celsius is a name. Centigrade, you hear centi meaning 100. All right. And you can see here we have a scale from 0 to 100. All right. When the centigrade scale was first made, actually they had 0 there and 100 there. That was later reversed. Okay. Thankfully, this is easier for me. A bigger number for a hotter temperature. But the idea was this. Okay. The idea is that one should be used for the freezing point of water. One should be used for the boiling point of water, because 0 and 100 are two really easy numbers to remember. Okay. And basically that idea has stuck. Okay. In the Celsius scale, 0 is where water melts or freezes, and 100 is where it boils or condenses. All right. So using that knowledge, that's how this temperature factor came about. Okay. We had to do an adjustment of 32 because we need to subtract out that 32 to to make sure that ends up being a 0. And based off of that, to end up with a 100, we needed to scale it by 1.8. Okay, thought of another way. Okay, 212 minus 32 is 180, and 180 divided by 100 is 1.8. Okay, you need to know that in a Chem 101 course? No, but I know some of you are curious, so I just thought I'd leave that part in there. All right, and then you continue on with that mathematics, you end up with this negative 273.15 as the lowest temperature possible. Seemingly random number, but yeah, that's how it works. All right, cool. So maybe you're feeling like, okay, now we have two scales. We're done. Okay, this one's convenient because it centers around water. Okay, it centers around water, and because water is such a common substance in life or in the lab, this also works great for just life itself. Okay. Okay, good. So we have two temperature scales. Why on earth do we have Kelvin? All right. As you'll see later on, if you're doing some gas calculations, okay, there's these interesting properties with gases. Okay, one of them being the more you heat up, let's say we have some gases trapped in a balloon, all right, and the more we heat up this balloon, assuming we're at a constant constant pressure and a condition, okay, and the same amount of gas in there, you heat it up, you can see what's the word? Balloon expand. All right. Now, an issue becomes where if you were to put a temperature into the equation and you were to put a negative temperature into the equation, it would imply that you have a negative amount of gas. Okay, you can't have negative particles. You can just have 0 particles. So to correct for that, we can use a Kelvin scale. All right. So the long story short, with Kelvin, Kelvin developed the Kelvin scale so that we could see temperature starting from 0 and then going up from there, eliminating the possibility of negative numbers and therefore nonsense scientific results. Okay, all Kelvin did simply, okay, some simple math, and you get a nice temperature scale named after you. Not bad. He just said, hey, the Celsius scale works great otherwise. Let's just add 273.15 to it so we can end up with a clean 0 for the lowest temperature possible. And now we can call no thermal motion at all absolute 0. Okay, 0 in multiple senses of the word. All right. So hopefully that explanation helped. But again, for most of you, I'm guessing you just care for doing the math at the end of the day. So hopefully this video was a mix of both the practical and the why of the 3 temperature scales. All right. Any questions, feel free to comment, and I'll go ahead and read those. All right. Thanks for watching. Take care.